Alright guys, it's Mr. Lynch. Let's get going on 2.1a, proportional relationships. But first, as always guys, make sure you hit like, make sure you subscribe, and make sure you guys are ringing that notification bell so you guys can see these videos as soon as they come out if you guys are watching this on YouTube. So, in the previous chapter we wrote equations with one variable to describe many different situations mathematically. Now we're going to start moving into writing equations that has two variables to represent a situation. So one variable represents one thing in a real life relationship and one variable represents the other. Now in the previous grades, you guys have studied proportional relationships and shown these in very different ways. So we're going to start off by just looking at some things that are going to help review for you guys and hopefully are just a review. So Julie is picking teams for her flag football team. She picks 3 girls for every boy that she picks. So, looking at this table below, if we pick one boy, then that means there are 3 girls. Because remember, it's 3 girls for every boy. So if we have one boy, then there's 3 girls. All right, so what about if there's two boys? Well, if there's 2 boys, we need to pick another 3 girls. I don't know why I wrote 3 there. I should say 6, because 3 plus 3 is 6. Now, if I have 4 boys, we picked 3, then 6, then 9, we must now have 12 girls on our team. Because every time I pick one more boy, we're adding 3 more girls, which means here we need to have 3 boys when we have 9 girls. So now we need to graph this. All right. So in graphing, I hope you guys remember, it's something called tails. So we have title. We'll just call this teammates. Right, because we're looking at the number of teammates that we've got. Axes. All right. So we have our x-axis here, which is given by boys. So we have our boys. Oops. Need to erase that. So we have, if we look down here, on the x-axis, we have boys. On the y-axis, we have girls. So title, axes, intervals, labels.
There's a testing.
And then S is scale. So with this, label our x-axis and our y-axis, our scale and our intervals. So with girls, we were going up by 3 every time we increased 1 on the boys. So let's increase the boys by 1. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so we've got our title, we've got our axes, we have intervals, we have labels, and we have the scale. The scale is the same. We're increasing by 1 on the x, we're increasing by 1 on the y. Now, if you guys remember, if we look back at this table here, when we have one boy, there are 3 girls. We're going to go over 1 and up 3. That says we have 1 boy and 3 girls. When we had 2 boys, there were 6 girls. So we're going to go up to 6. When we had 3 boys, there were 9 girls. So 3, we go up to 9. And then when we were at 4, we go up to 12. Now you guys might start to notice that looks like a pretty straight line that goes through these points. I wonder what's going to happen here. So this is the relationship, right, guys? For every 1 boy, we have 3 girls. So find the ratio of girls to boys for several different ordered pairs. So if we look at this, right, if we look at our ordered pairs are, remember it goes X then Y, right? Every ordered pair is written as X then Y. So we go over 1, then we go up 3. Our next ordered pair, we're at 2 to the right and 6 up. Our third ordered pair, we're going 3 to the right. So our X value is 3, and our Y value is 9. And then lastly, we have 4 boys and 12 girls. It's always X, then Y. This is what ordered pairs look like. And a really cool thing before we move on from there, from looking at those, the ordered pairs also came from this table, guys. So this table of comparing boys to girls gave us those ordered pairs. So we need to find the ratio. So if we take the number of girls divided by the number of boys, well, girls are this y coordinate. So I'm going to take 3 and divide by 1. Well, 3 divided by 1, that's easy. That's just 3. Okay, let's look here. Let's look at the second one. So I have 6 girls and 2 boys. Well, if we divide 6 by 2, that gets us 3. That's really weird. All right, I'm going to try the last one because this is too weird for me, guys. So we take 12 divided by 4. 12 divided by 4 is 3. That's really weird. Why would these all be 3? That doesn't make sense to me. So the relationship between the girls and the boys. Well, we know that for each boy, we get 3 more girls. So I'm going to say that we're taking our number of boys, multiplying it by 3, and getting our number of girls. And we can see that too if we look at the ratio of girls to boys. So the number of girls divided by the number of boys gets us 3. That's where we get this 3 right here from. All right. This is that relation that exists between the boys and the girls. So now let's use the equation and the graph to determine how many girls would be on the team if Julie chooses 10 boys. Wow. So we have girls are equal to 3 times our number of boys. Okay. So if we have 10 boys, then the girls are going to equal 3 times 10. Well, 3 times 10, that's easy. That's 30. So then we'll have 30 girls. And if we were to look back at this graph, if we kept going up this way, by the time we hit 10, we'll be way up here at 30. Pretty cool, right, guys? Okay. So use the equation and graph to determine how many boys are on the team if Julie chooses 18 girls. So this is a little more difficult here, guys, because we have 18 girls. And again, we're using this same equation here. So 18 equals 3 times the number of boys. Well, we don't know how many boys there are. How are we going to solve this? Man, it's almost like we've been doing stuff like this for weeks now in order to get you guys prepared for this. Let's say, I'm going to make boys. I'm going to make a variable for boys. I'm going to call it x. So 18 equals 3x. How do I solve for x here, guys? Well, it's easy. All we have to do, divide both sides by 3 to get x by itself. So then x equals 6. So if there are 18 girls on the team, there are 6 boys. Now, if we want to use the graph, if we look back over here, well, at 4 we had 12 girls. At 5 we're going to have 15 girls. So then at 6, if we go all the way up here, we're going to have 18 girls. And it should be right about there. So if we look at the graph, if we follow this line that we're kind of creating here, at 6 we should have 18. And again, guys, this graph also goes through the point 0, because if there are 0 boys, there's going to be 0 girls. Okay, so we looked at proportional relation. Now, when two quantities are proportionally related, the ratio of each y value to its corresponding x value is constant. This is called the constant of proportionality, or the proportional constant. So if we look back up here, this 3 is that constant of proportionality. Which is a really big word. Constant of proportionality right here is 3, because we constantly get 3 from each of the proportions that we build. See, each of these proportions right here, number of girls to number of boys, this constantly gives us the number 3. So 3 is our constant of proportionality. Now we're going to skip this whole problem here, and we're just going to jump right here to unit rate. So every ratio has an associated rate, and the unit rate is another way of interpreting the ratio's proportional constant. So if y and x are in proportion, then the unit rate of y with respect to x is the amount of y that corresponds to 1 unit of x. Now, this is kind of, just giving you guys a lot of x, y, and it's kind of abstract here. But if we go back to what we were looking at with the boys and girls, so if the quantities y and x, so if we call y girls, and we call x boys, then the unit rate of girls with respect to boys is the amount of girls that corresponds to 1 unit of x. So our unit rate in that last problem was 3, because with each unit of x, with each increase of 1 boy, we gained 3 girls. And if we interchange the roles of x and y, we could speak of the unit rate of x with respect to y. So that would be, how many boys do we get on the team for each 1 girl? Which physically doesn't make sense, because it would be 1/3. You can't have a third of a person. I mean, if you have a third of a person, that's kind of a problem. All right. So number 7 here, let's look at this new problem and proportional relationships in unit rates. So we're pouring cement in our backyard. That's 100 square feet. The cement comes out of the truck at a constant rate, and it's very important that the cement gets poured by noon, or it gets too hot for the cement to be mixed properly, and then it just turns out bad. So it's 11 a.m. We have 1 hour. It's 11. And we've poured 75 square feet out of the 100. And we've poured it in the last 3 hours. So at this rate, will we finish before noon? Okay, so we've poured 75 square feet in the last 3 hours. So we're looking at square feet and hours. So what we're going to do is we're going to look for a unit rate of square feet per hour. So we want to know how many square feet are we getting, square feet are we getting per hour. Well, if we poured 75 square feet in a total of 3 hours, then our unit rate, or our rate per hour, is going to be 25 square feet per hour, right? We take the total amount that we poured so far, we take our square feet amount, and we divide it by how many hours it's been. So, and of course, at 0 hours, we had 0 feet poured. I mean, we hadn't poured anything, so we couldn't have any square feet. We haven't even started yet. So then if our elapsed time is 1 hour and we're moving at 25 square feet an hour, the amount of concrete we've poured is 25 square feet, because that's 1 unit. It's 1 unit of time, which gives us our unit rate of 25 square feet that we have now poured. After 2 hours, we poured 50 square feet. And after 4 hours, which gets us to noon, we have poured the full 100 square feet. Now again, we need a title. So let's title this cement. Here's our y-axis. Here's our x-axis, which is time. And actually, I'm not going to write that off to the side like that. I'm going to write that completely underneath. So down here we have time. And over here we have square feet, or feet squared. So we have our square feet, we have our time, we have our x-axis and our y-axis. Well, the amount of our time, we're going up by hours. So I'm going to do 1 hour, that's 2 hours, 3 hours, 4 hours, and 5 hours. Now, I can't really do that for our y-axis. If I do that for our y-axis, if I go up by ones, we're not going to have enough. So what I'm going to do is I'm going to go up by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to go by tens. Now, the reason I chose to go by tens was so that at the very end, at this 4 hours, we'd be up here at 100 square feet poured. And at 2 hours, we're up at 50 square feet poured. At 0 hours, so 0 for our x, we have a 0 for our y. Remember, guys, this is giving us that ordered pair. It's 0, 0, 1, 25, 2, 50, 3, 75, 4, 100. These are our ordered pairs. I'm going to put the commas in here. So then at 1, we must go up to 25. And I'm going to do my best to put a 25. At 3, we're up at 75. I'm going to do my best to make it 75. So now if we were to draw a straight line, why won't this move? All right, that looks like it's good. All right, so I'm going to get rid of my ruler, and you guys can see we have a straight line through all of these. So our unit rate, or how many square feet can we pour in 1 hour, is 25 square feet per hour. Because every hour we pour 25 square feet. Now, which equation given below best describes this relationship? I want you guys to choose which equation this is. All right, you guys may need to remember what is x, what is y, what does it represent? Okay, is x the cement or the time? I don't remember. And then you guys need to justify, will Doug finish the job in time? Okay, so guys, let's look at this. Does the graph describe a proportional relationship? Is this a proportional relationship? Well, what we need to know in order to answer that is, one, does it go through 0, 0? So is 0, 0 a point on this line? That's really important. If it doesn't go through 0, 0, it is not a proportional relationship. So this graph, yes, it goes through the point 0, 0. 2, is there a unit rate? Does this have a unit rate? Well, it seems like we go over 1, up 3, over 1 and up 3. And it looks like for each increase in our scoop, we are gaining 3 ounces. We can clearly see that from this graph. Has a unit rate. So guys, this must be a proportional relationship. Yes, this does describe a proportional relationship. What is the unit rate for this? Well, if we look at this, we increase 1 scoop, we increase 3 ounces. If we have 2 scoops, we have 6 ounces. If we have 3 scoops, we have 9 ounces. Can we say that 9 divided by 3 is equal to 6 divided by 2 is equal to 3 divided by 1? Can we say this? Is this true? Because if it is, then we can find our unit rate by dividing any of these. And I think our easiest one to see is 3 divided by 1, which gets us a unit rate of 3 scoops. Sorry, I was wrong there. 3 ounces per scoop. Okay, and then you guys are going to need to explain how you can find a unit rate at a different location on the graph. Now we need to write an equation. So remember, guys, we need to compare the ounces to the scoops. Well, is it 1 scoop is 1 ounce? I don't think 1 scoop is 1 ounce. And if we look at that, we said it was 3 ounces per scoop, which means our ounces are equal to 3 times our number of scoops. If we're looking back at the first problem we did, guys, remember we said that our girls were equal to 3 times our number of boys. And we were looking at the relationship of girls to boys. Okay, so you guys are going to finish this off by yourselves. You guys are good to go. Trust me, I've imparted every bit of knowledge that I can into you guys. So guys, as always, enjoy the math and have a great rest of your day.